Okay, hello everyone. Now it's time to start the regular the session. My name is Shinji Watanabe, Carnegie Mellon University. I'm chairing this session, and this the session is composed of the four the regular talk. It can be 10 minutes per each, and the rest of the 10 minutes will be the use for the Q&A. So if you have any questions, that is really welcome. But if you type it in the chat, then we can catch up your questions in the question and answering time. Okay, so the first, let's move to the first the speaker. The first speaker is the Wenjin Fan from Nagoya University, and the title is the S3PILBC Open Source Voice Conversion Framework with Self-supervised Speech Representation. Wenjin, can you share the screen? Is it possible?
Yes.
Okay.
Okay. Can everyone see the presentation in the presentation mode?
Yes.
Okay. So my name is Wenjin Huang. I'm from Nagoya University from Japan. Today I'm going to present this paper called S3 Parallel VC Open Source Voice Conversion Framework with Self-supervised Speech Representations. This is a joint work with the Superb team, but the members mainly come from National Taiwan University from Taiwan and CMU from USA. So first, we briefly introduce what we try to do in this paper is voice conversion. It is a technique that converts one kind of speech to another without changing the linguistic content. So if you think about the nature of voice conversion, there is this trending paradigm that is called recognition synthesis based VC. So you look at this figure, then it's easy to imagine that one way to do VC is to first start by recognizing the contents that is being said from the input speech. So we extract the contents first, and then we synthesize the speech of the target. Okay, so basically we can write this equation: the converted speech equals to the input speech minus the source information plus the target information. So we can use two modules, a recognition module and a synthesis module, to realize this kind of recognition synthesis based VC paradigm. For example, we can just simply cascade an ASR model here and a TTS model to form such a system. This kind of paradigm has been greatly adopted by many state-of-the-art systems in the Voice Conversion Challenge 2020. So this is how it works in the training and the conversion phase. So first, we will train our recognizer using either labeled or unlabeled data set. Then we use this recognizer to extract speech representation from a target speaker data set, for example. And then we also extract acoustic features. These are something that we want to generate. So this is the input, this is the output, and we train a synthesizer to map from the representation to the acoustic features. So after these two modules are trained, during conversion phase, we start with the source speech, and we use the trained recognizer to get the speech representation. And then we use the trained synthesizer to get the converted acoustic features. And finally, we use a waveform synthesis module or something like a neural vocoder to synthesize the converted speech. In terms of the intermediate representations, we have several options. So previously, people have been using supervised speech representations such as text or phonetic posterogram, PPG. So the difference between the text and the PPG is basically in terms of the resolution. So text is basically token level, and the PPG is basically frame level. The good thing about this kind of speech supervised representation is that they're very accurate, because we just explicitly say that we want the contents to be extracted. But the bad thing is that we need label data to train these recognizers. So recently, people have been looking into using self-supervised speech representations, S3Rs, to use them as another solution to these supervised representations. So we basically learn, rich and compact presentations from large scale and label data. So we think that VC is a good proxy task for SGR because that previously we have been only studying discriminative tasks such as ASR or ASV, but it remains unclear what kind of SGR are optimal for generation tasks such as voice conversion. So we hypothesize that if we look at this figure, we may see that a good SGR for VC might be something that is rich and compact in content, but it needs to contain as little to none on speaker information so that all the source information can be removed at the first stage, and then so the synthesizer can add the target information back to the contents to form the converted speech. So based on all these insights and observations, we decided to develop SGR VC as an extension of the SGR toolkit and the super benchmark. So evaluate SGR-based VC in a very unified setting. We use one unified data set. We evaluated several tasks, and then we unified the implementation and also the evaluation metrics, and we compared them with several top systems in VC 2020. So the data set was VC 2020. It has two tasks. Number one is intralingual VC, and number two is cross-lingual VC. So in cross-lingual VC, we have training utterances from different languages. So that's why we call it cross-lingual, because we want to synthesize target where it did not really have ever spoken English before. So it's like this kind of target does not exist in the training set. So we consider here any-to-one and any-to-many voice conversion. Any-to-one is about converting from unseen speaker to seen speaker, and any-to-any is about converting from unseen speaker to unseen speaker. So this is considered a harder task in VC, and we consider intralingual and cross-lingual settings in any-to-one, and any-to-any we only consider intralingual setting. The implementations we used basically resembles top systems in VC 2018 and 2020. And basically they are just stacks of convolution layers and RNN layers. For the competing systems, we used a collection of SOTA recognition synthesis-based VC systems. They all use PPGs, they used pre-training on the multi-speaker dataset, and they also used autoregressive vocoders like waveness. So it makes them very, very strong in terms of the quality. For the evaluation metrics, we used several objective measures such as male caption distortion, MCD. This is L2 norm based, and WER from a pre-trained wave-to-wave model. This is measuring the intelligibility, and separate from an ASV model. This is basically to assess the conversion similarity. And we also evaluate naturalness and similarity from a listening test. So here are the results. First, we compare different kinds of models, and these are very detailed, but what we want to say is that we've finally come to use a more complicated model, and we show that this kind of more complicated model can balance between, for example, intelligibility and conversion similarity, because these two are often two very competing factors in terms of voice conversion. And secondly, we compare different tasks. So intralingual VC is considered easier than another task, for example, like cross-lingual VC. And we can indeed see that this kind of trend in all these upstream models, all these SUR models, this trend is basically observed. And another thing is that intralingual any-to-any VC is also considered harder than any-to-one because you need to convert to unseen speakers. And basically in all the upstream models that we used, we only found one model to work well, which is the VQ wave-to-vec, and it could achieve reasonable WER and ASV scores, while the others were very, very bad in terms of ASV scores. And we compared to SOTA. Unfortunately, that we found, although the numbers did not really seem to be very different in terms of the naturalness and similarity from listening test, our best system in terms of SUR methods, it's just much, much worse than the SOTA methods. This is basically because that they used better vocoders, they used more data to train their models, and there are still a lot of to improve when it comes to comparing from self-supervised representations and supervised representations. Finally, we want to justify the objective metrics we use. So we calculate the linear correlation coefficients between different metrics, and we found that MCD is actually correlating very well with naturalness and similarity. So that in the future, when we want to evaluate more upstream models, we can just simply use MCD to evaluate how good that upstream model is. So we have some samples and code base all on the internet, and then you can just use these QR codes to simply listen to the samples and use our code base. So we have some future research directions for both the VC people and the S3PR people. For VC, we think that it is worthwhile to improve this kind of S3R based VC. For example, using better downstream model, or using better vocoder, using better waveform modeling techniques, and so on. And in terms of S3R, we found that, as we've shown in the previous slides, that, for example, only VQ wave-to-vec worked well for any-to-any VC, and all the other models basically kind of like fail. So it is indeed worthwhile to improve these upstream S3R methods. And then we can analyze what kind of components are key to voice conversion. For example, on VQ wave-to-vec, maybe it's because that it has these quantization modules in this model component, so that it can be disentangling the speaker and the content information properly. That's causing it having a very good performance in voice conversion. Yeah. And I think that's all. Yeah. So thank you for listening.
Thank you so much. Okay, and again that we will have a question answering phase after all the presentation. So if you have any questions, please type it. So Ryota, can you please start to share the screen?
Okay.
So the second presentation is pronunciation adaptive self-speaker agent, self-speaking agent using WebGrad. And the presenter is Ryota Komatsu from Tokyo Institute of Technology.
Okay, I'm Ryota Komatsu. This is joint work with Tomohiro Tanaka, Takuma Okamoto, and Takairi Shinozaki. We introduced a pronunciation adaptive self-speaking agent using WebGrad. Human babies are born without knowledge of any specific language. They acquire spoken language from scratch through observation and dialogue. Without relying on text labels, they realize a closed learning loop in human society. With this learning ability, they can adapt to a variety of changing environments. In this work, we try to equip such an ability to the agent. As a pioneering work in spoken language acquisition, Gorin et al. Proposed an automatic code routing system that runs a vocabulary and action from scratch. The system automatically finds new words in the input utterances and adds them to the recognition vocabulary. The system's action is code routing, and the system runs the correct routing from the user's feedback. However, the system's limitation were that it could only handle speech input, and it could work only with only a predefined action space. Taguchi et al. Proposed a robot system that can learn new location names from spoken utterances, and grant them with the locations and pronounce them based on co-occurrences. However, the system needs a pre-trained phoneme recognizer and speech synthesizer, which requires labeled speech data. Hattori et al. Proposed a robot arm system that runs learn to pronounce spoken instruction. It can grant spoken words with its image objects and can learn required movements by reinforcement learning. However, it needs a pre-trained speech recognition system to transcribe speech utterance and does not support new word discovery and pronunciation learning. As our previous works, Chang et al. Proposed the agent supporting all the elements. Word discovery, semantic grounding, action running, and pronunciation running. For word discovery, the agent makes sound dictionary by segmenting continuous sound and use it as an action space. For semantic grounding, the agent runs the correspondence between image and sound by triplet row-spaced running. For action running, the agent runs the effect of speaking words in a reinforcement running framework. And for pronunciation running, the agent selects and speaks elements in the sound dictionary. However, one limitation of Chang's system is pronunciation adaptability. Chang's agent uses a sound dictionary as an agent speech organ. It's discretizing the action space of speech of utterance pronunciation and makes the reinforcement running efficient. However, it cannot adapt pronunciation other than changing element selection. For this problem, we propose to use a neural vocoder as agent speech organ. To train a neural vocoder, there are some methods. The first one is unconditional training. In this method, it generates waveform only with random sampling. And the generated sound is like human babies babbling, but not word. This example is generated by WaveNet. Sorry.
Cannot hear the sound.
Sometimes he's just in a thing from stage. It's now being times. So the double 30 cam and this means the
second one is semi-conditional training. In this method, a neural vocoder is conditioned on time invariant information, such as word ID as in diff wave. Because the agent action space is discrete, we use this method. Our proposed agent trains a neural vocoder in a self-supervised running framework. First, the agent uses the sound dictionary. During the dialogue, the agent accumulates successful action sound dataset. Then, it trains waveguard by this dataset. After training of waveguard, the agent starts to use it and periodically update it by the successful dataset. So the agent can adapt its pronunciation in a variety of changing environments. To evaluate our agent, we use a full task. In the observation phase, the agent hears a long utterance containing food names. Then, the agent observes food images with its audio descriptions. In the dialogue phase, the agent is shown two food images. If the agent the agent's utterance is one of their names, it gets the food. And the food is the agent's desired one, it gets the positive reward. Experimental setup is the following. We use a Chang's system as a baseline. And in the image dataset, the food type is 8, and the number of training images is 90 per each food. In the observation phase, audio description is generated by Google text-to-speech. The types are food, a food, a color food, and it's a food. And in the dialogue phase, the dictionary size is 20,000, and we change the noise condition at 120,000 episodes. These are the average reward in the dialogue phase. When the environmental noise is steady, the performance of sound dictionary and wavegraph is almost the same. However, when the environmental noise changes, the wavegraph outperforms sound dictionary. This is because the sound dictionary-based agent can only select the element in the sound dictionary. The following example is generated by the wavegraph.
Green pepper, lemon, tomato, sweet potato, potato, orange, cherry, strawberry.
As summaries, we proposed a pronunciation adaptive spoken language acquisition agent using wavegraph. The wavegraph running is embedded in the self-supervised learning approach. The agent can automatically adapt its pronunciation to a changing environment. As the future works, we improve the sample efficiency of the pronunciation adaptation by introducing model adaptation techniques, and supports multiple utterances by extending observation and dialogue writings. Thank you for listening.
Okay, thank you so much. And again, please put your question and to the chat window so that we can collect the information about QA. Lian-Xuan, are you ready to share the screen? Okay, so the next the presentation is Mandarin English code switching speech recognition with self-supervised speech representation models. And the presenter is the Lian-Xuan Chen from National Taiwan University.
Okay, hello everyone, I'm Liang-Xun Zhen. Today I'm going to talk about our recent work, Mandarin English code switching speech recognition with self-supervised speech representation models. This work is co-authored with Yuquan Fu, Henrui Zhang, and instructed by Professor Hongyi Li from National Taiwan University. And this is my outline for today's presentation. First, I will give you an introduction of our research topic. Second, I will describe more details of the methods we used. Finally, I will show you our experiment results. So, what is code switching? Code switching means alternating between two or more languages in speech. Here, we have an example. As you can see, the orange words are in Mandarin and the blue ones are in English. Code switching talking style is quite common in some countries. Here, we mainly focus on Mandarin English code switching, which is frequently used in East Asia, like Taiwan and Singapore. And what are the difficulties of code switching ASR? First of all, the data sparsity. We have large monolingual data sets, but the code switching data sets are rare and relatively small. Second, identifying languages between words with similar pronunciation is very hard. For example, the English word go sounds almost the same with the Mandarin character, go. In order to tackle the difficulties, we came up with the idea of using self-supervised speech representations. But what are the advantages of using these representations? First, the self-supervised model are trained on a huge amount of data. It might bring some benefits to the code switching ASR, which has data sparsity issue. On the other hand, most of the self-supervised models have transformer architecture, so there might be more contextual information in their speech representations. With these high-level speech representations, it might be easier to identify languages. So these are the reasons of why we want to use speech representations to deal with code switching problems. In the next section, I will describe our methods, including how we extract speech representation and our frameworks on some code switching tasks. Our method to extract speech representations is referenced from Superb. We obtain them by weighty sum the transformer layers outputs in the frozen self-supervised model. To be more specifically, we adopt Web2Vec2 as our self-supervised model to extract speech representations from. And this is not only because it is powerful, but also because it provides multilingual and monolingual models to train with similar amount of data. After introducing our method to extract speech representations, let's talk about a CTC module we use for the code-switching ASR. We first extract the speech representations from Web2Vec2 and then feed them into the by LSTM downstream model. Therefore, we can obtain the CTC outputs and calculate CTC loss on them. This is a simple CTC framework, but with speech representations as input. Besides of code-switching ASR, verifying language identity, or LID, is also considered as a common technique to help tackling code-switching problems. So we also want to see if the model can perform better with these representations than some traditional features. The LID task we talk about here is frame-level LID. Each frame of a utterance has to be classified into one of the least three classes: Mandarin, English, and Silence. Now, let's introduce our LID module. As you can see, the framework is very similar with the CTC module. Besides of bidirectional LSTM, we also use fully connected network to explore the power of speech representations. And since the LID task is more like a frame-level classification, we use cross-entropy loss for our loss function. After finishing the experiments on the CTC and LID modules, we start to think about the connection between them. We are wondering if the LID module can benefit the CTC module or not. And we are not the first one to think that the LID module can help improve the performance of code-switching ASR. In 2019, Li et al. Proposed a decoding method to further improve the code-switching ASR performance. Here, we make a simple demonstration. We draw the composition of one frame of the CTC and the LID outputs. The methods generate new CTC output probabilities by directly multiplying LID probabilities to the corresponding CTC probabilities. Finally, we directly decode on these new generated CTC outputs. And based on the method mentioned in the previous slide, we proposed a new method that can train the LID and CTC modules jointly. Instead of multiplying, our method is to add LID logits to its corresponding CTC logits, and then jointly fine-tune by CTC loss. We will show the results of these methods later. In the experiment section, I will first talk about what dataset we use, then present the results of our experiments and give more insights of our proposed method. So we use a Mandarin English code switching corpus called CME as our dataset, and the language distribution is shown in the table. CME corpus contains two testing sets. The DevMan testing set is dominated by Mandarin, while the DevSGE is dominated by Singapore English. And since there is no LID labels in CME corpus, we have to generate by our own. So let me describe our procedure. First, we pass the paired speech and text data into Montreal Force Aligner to find word boundaries. Then we use the boundary timestamps to generate language ID frame by frame. Finally, we save the LID labels to train our LID models. And this table shows the results of code switching ASR with only CTC module, but using different input. Our evaluation matrix is token error rate, which is similar with word error rate, but compute on token instead. Each token is either Mandarin character or English word. As the table presented, models that use speech representations outperform traditional FBank by over 30% relative token error rate. Furthermore, the multilingual pre-trained version produced the best performance. Next, let me show our results on the LID task. You can see that the fully connected network performs badly when using FBank as input, but with the speech representations, it can score on over 70% high accuracy. Furthermore, BiLSTM with multilingual Web2Vec2 got the best performance, over 90% on both testing sets. These results encourage us to take the experiments of the jointly training framework, hoping that such high performance on LID can bring some benefits to the code-switching ASR. Finally, this table shows the results of our jointly training framework compared with other baseline. The first method is using only CTC module. The next method is to directly multiply LID probabilities to CTCs. However, this method is worse than the CTC-only method. But with our proposed method, which is to add LID logics to CTC, then jointly fine-tune, can get the best results among all. And to give more insights of why our methods perform the best, we present an example to give some analysis about it. First, we draw the LID outputs probabilities. The orange line indicates the probabilities of Mandarin, and the blue one indicates the English. The reference texts are shown below the time axis. Notice that the correct English word is break in this example. Next, we draw the CTC probabilities on the same plot. These CTC probabilities are obtained after multiplying the LID probabilities. As you can see, the Mandarin word "bu" still cannot be brought down directly by multiplying LID probabilities to it. Furthermore, because the CTC outputs tend to have some latency, the probability of the Mandarin word "yao" is compressed by the misalignment between the CTC and the LID outputs. But after our jointly training method, the LID model learns how to justify its output. As indicated, the LID outputs now have a small time shift to fit in the latent CTC outputs. Now, the Mandarin word "yao" is not compressed by LID outputs anymore after jointly fine-tuning. Moreover, the English word "break" had been successfully brought up by the LID logics. So after presenting analysis on our proposed method, I would like to make some conclusions of our works. First of all, we verify that self-supervised speech representations can perform well, even in code-switching scenario. Second, multilingual pre-trained model gives the better performance than the monolingual pre-trained one on our code-switching tasks. Finally, we proposed a method to further improve the code-switching ASR performance by jointly training with the LID module. That's all for today's presentation, and more details can be found in the paper. Thanks for listening.
Thank you so much. Yan, can you start to prepare your presentation? Okay, the last presentation in this the session, don't speak too fast. The impact of data bias on self-supervised speech models. The presenter is Yan Men, National Taiwan University.
Okay, I'll start my presentation. Hello, everyone. My name is Yan Mei. I'm here to present our paper, Don't Speak Too Fast, the impact of data bias on self-supervised speech models. This paper is co-authored by Yihui Cho, Andy Liu, and Professor Hong-Yi Lee. This is the outline of our presentation today. First, I will talk about the background and motivation of our work. In real-world applications, our collected audio data can be biased in different aspects. For example, data can be demographic biased, which is the data may be gender imbalanced or falls in specific age range or accent. The content of audio data can also be biased. Conversational data versus spoken literatures will have a huge difference in word choices, resulting in content bias. Prosody is also a very important element in speech. Audio data may have varying speech rate, tone, or other prosodic features. Training on biased data may possibly cause some fairness issues or possibly result in performance drop. So data bias have become more aware in recent research. There are previous works investigating data bias of a single downstream task. However, data bias in self-supervised pre-training is unexplored. In most of the previous works, self-supervised speech models are pre-trained on standard data sets such as libre speech, which is carefully collected and designed for speech modeling tasks. We are hence curious about how would data bias in pre-training affect self-supervised speech models' performance? And also, is balanced data for pre-training necessary to achieve good performance in downstream tasks? Our work would give insights to these questions. And now is the introduction of our work. Our work analyzes the effective data bias in self-supervised speech models. We study three aspects of bias: gender, content, and prosody. So our experiments will be split into these three sections to discuss. And for each experiment, I will introduce how we design our biased data sets and the evaluation results on downstream tasks. Now let's move on to our methodology. There are two phases in our workflow. The first phase is self-supervised pre-training. We first pre-train our self-supervised speech models on biased datasets of these three aspects: gender, content, and prosody. And for the self-supervised speech models, we select two models from different families, which is Terra and APC. And then is phase two. After pre-training on biased datasets, the weights of the self-supervised speech models are frozen, which is served as a frozen feature extractor. The extracted representations will be evaluated on 5 downstream tasks selected from the super benchmark. These 5 tasks are phoneme recognition, keyword spotting, speaker identification, intent classification, and emotion recognition. They fall in 4 categories: content, speaker, semantics, and paralinguistics. Note that the tasks we select utilize only a simple linear model so that the quality of speech representations can be directly and better investigated. And now let's talk about our experiments. Our pre-training data is fixed to 100 hours in all experiments. We use the libre speech 100-hour subset and the 360-hour subset to design a total 100 hours datasets with different biases. The first experiment is gender bias. For the bias datasets, random sample total 100 hours of audio of these 6 imbalanced gender ratio settings from the original libre speech 100-hour subset and the 360-hour subset. The settings, for example, 10 to 0 means that the bias dataset is composed of all female audio, denoted as all F, and 9 to 1 represents 90% female and 10% male, denoted as 9F1M. Consider randomness in speakers. We random sample 3 datasets for each setting. And for the baseline of our gender bias experiment, we use the original libre speech 100-hour subset plus 3 random sample datasets with equal gender ratio, denoted as 5F, 5M. And when testing on downstream tasks, we split the testing data into male and female subsets if demographic information is provided. Now is the evaluation results on downstream tasks. The figures contain many information, so I will first briefly explain how to interpret the figures. The horizontal axis denotes different gender ratio setting, and the y-axis denotes phone error rate for phoneme recognition and accuracy for speaker identification. The left of figures is the results using Terra, and the right is using APC. The green points are the original testing results, and the orange points are the testing results on the female subsets, and the blue is on male subsets. And the lines are obtained by connecting the average of the 3 random sample datasets of each setting. As shown in the figures, phone recognition with APC and speaker identification with both models are more affected by gender bias, which is that the performance degrades as the gender ratio of the pre-trained data set becomes more extreme. But we can also observe that by adding 10 to 20% of data of the opposite gender can effectively bridge the gap between the testing accuracy of the male and female subsets. And the remaining 3 tasks are comparatively relevant to gender bias. As we can see from the figures, that the balance setting does not necessarily achieve the best performance. And there is no obvious correlation between the performance and the gender ratio setting. After evaluated on downstream tasks, we surprisingly found that even when trained on extremely biased datasets, the effective bias in downstream is rather small. So we further inspect the representations extracted by the self-supervised speech models pre-trained on different gender biased datasets. We extract the representations of the utterances in the libre speech test clean subset. We view each time step as a data point, and we calculate the average similarity score of the representations between each pair of models. We adopt the method projection-weighted canonical correlation analysis to calculate the similarity. This is the similarity heat map, and the number following the setting name indicates different random sample data sets. As we can see from the figures, the extracted representations of Terra pre-trained on different gender biased datasets are highly alike, while the representations of APC pre-trained on datasets with more similar gender distribution have higher similarity scores, which is the lighter block at the upper left corner and the bottom right corner. However, in both models, gender bias in pre-trained data has only a slight effect in downstream. As a result, we may conclude that there is no direct correlation between representation similarity and the behavior in downstream tasks. Okay, in the second experiment, we're going to discuss the effect of content bias. We designed 2 data sets for the content bias experiment. We first calculate the perplexity of the transcription of an utterance measured from the libre speech official language model. And then we select 100 hours audio with the highest perplexity, denote as PPL high, and 100 hours audio with the lowest perplexity, denote as PPL low. PPL high contains rarer words and more proper nouns, while PPL low is mostly composed of common and simple words. And for the baseline, we simply use the original libre speech 100-hour subset. The results are shown in a red box. The bold text represents the best result of the column. Pre-training on these 2 content bias datasets has a slight performance drop in most tasks compared to the baseline. However, either higher or lower perplexity datasets did not result in greater performance drop, suggesting that content bias would not affect the pre-training of self-supervised speech models much. And the next section is the prosody bias. For the prosody bias experiment, we designed 4 datasets. Speech rate can be viewed as an important prosodic feature, so we first create 2 bias datasets to study the effect of pre-training on relatively high or low speech rate. We calculate words per minute of each utterance, and we get 2 100 hours datasets with the highest and lowest words per minute, denote as WPM high and WPM low, respectively. We further create 2 datasets with extreme speech rate. We convert the playback speed of the libre speech 100-hour subset 2 times faster and 2 times slower, denote as speed 2x and speed 0.5x. And for a baseline, we use the original libre speech 100-hour subset. And as we can see from the results in the red box, the self-supervised speech models perform poorly when pre-trained on 2 times faster speech rate. But pre-training on relatively slow speech rate achieve better results than the baseline in some tasks. And even pre-trained on extremely slow speech rate, which is the last row, the performance of the self-supervised speech models did not drop too much. And some tasks such as intent classification and emotion recognition even outperform the baseline. And finally is the conclusion of our paper. Though we can say that it is still best for self-supervised speech models to pre-train on well-collected and balanced data, as models pre-trained on the original deliberate speech 100-hour subset achieves the best performance on downstream tasks overall. But when there is some restriction in data collection, our work shows that pre-training data does not need to be gender balanced to ensure the best performance. And also content bias in pre-training does not affect much. And that self-supervised speech models somehow show a preference towards lower speech rate. We believe that there are other aspects of bias that can be further studied in the future. And this is my presentation today. Thank you for listening.
Okay, thank you so much. So now the question and the answering slot. So please type your questions to the presenter. So first question is from Daniel. Maybe Daniel, you can just directly ask her. Can you do that?
Yeah. First, thanks so much for the presentation for all the four. I have a specific question for the last one. Don't speak too fast. I'm curious. We saw like you try on like a Terra and the APC, but I'm curious. Do you expect to observe different kind of sensitivity to the three or more like a bias for S3 and models like with different complexity? I ask because in speech we observe like sometimes with more parameters, models with more parameters, usually they are more affected by the bias or they have balance. I wonder if that can be observed for like speech self-supervised models.
Yes, I understand that we only perform our experiment on small models because limited to our training resource or something, we can not perform this this kind of experiment on this kind of pre-training experiment on like with Vec2 or Hubert, such large models. Yes, but yes, I believe the results may be different if these experiments are performed on Hubert or with Vec2 with much larger parameters. Yes. The main concern is the training resources. Yes.
Makes sense. So I have a question to the second speaker. I'm actually very impressed this kind of entire system. And then my question is that easily reproducible? Are you guys actually make this the system available as our open source and the pre-trained models and so on?
Oh, yes.
We included the link at the end of our presentation slides.
And that includes the source code and so on.
Yeah, we use a OpenAI GEM framework to describe the environment and use the reinforcement library stable baseline 3. And some part is a little bit tricky, but we are trying to make it modulated and easy to extend.
Mm-hmm. Thank you so much. Yeah, that's very impressive work. So I would like to follow that.
Thank you.
Any other question? Okay, actually, from Hongi, can you speak directly or can I read it?
I can speak directly. This question is to the second paper to Tommaso. Any reason you use WaveGrid instead of other neural vocoder? Does the quality of the vocoder influence the experimental results?
Oh, because WaveGrid has less tuning factors, and for real-time speech synthesis, we use a WaveGrid.
Because we embed the learning in the automatic self-learning, the learning should be simple, and we found that it is very easy to train.
I see. Thank you very much. Thank you.
Thank you.
Maybe I can accept one or two questions and want to finish this session. Is there any other questions? Okay, so then for the question about, I have a question about the third presentation, code switching. I'm actually considering that it's good idea and maybe joint training is helping to solve the issue. But anyway, CTC is a model to spike the kind of the token, while the language ID part is frame level, the prediction, right? So I saw that it has some kind of how to say discrepancy, inconsistency due to the kind of behavior of the model. So I'd like to actually your the final question of the joint training is adjusting the CTC spiking the timing to the language ID frame level the information, I believe. So, but I just want to have a bit more expansion about the discussion whether these two models the originally differently behaves have the good kind of the benefit when we combine it.
Yeah, our experiments is actually jointly add LID logics to CTC logics frame by frame. We don't this question is very interesting, but I don't really I cannot come up a new idea of jointly training for dealing the spike and the spike in the CTC and LID frame level LID. This problem.
Yeah, but partly you actually solving this one, right? That's why the alignment is well adjusted. So I think the way you are doing seems to solve the issue, but I'm fundamentally interested, how we kind of adjust these two models. Yeah.
But we think that the LID output seems to be not that spiky as the output. So this mechanism, I think it won't change the spike of the CTC output.
Right. Yeah. Okay, thank you so much. And there's a couple of other questions, but I just want to finish this session. Thank you so much, everyone. And I just take over the chairing to Daniel.